For the problem, let's start off with number 25. For this one here, calculate and compare the energy of a photon of wavelength 3.3 micrometers and that of wavelength of 0.154 nanometers. So one of them is a little screwy, but we'll get through it. We want to look at the energy of these two photons. So I'm going to use the equation that we developed before in the previous lecture, which is E equals hc over lambda. These two guys on top, whoops, pull this down a little bit. These two guys on top are both constants, and this bottom one here is the one we're referring to, the wavelength. That's our variable that we're going to deal with. So let's do these ones separately. The first one, E is equal to, put Planck's constant in, 6.626 times 10 to the negative 34 joules times seconds, and that's times the speed of light, 3.0, times 10 to the 8th meters per second, and the variable for this problem here, 3.3, and these happen to be micrometers, so times 10 to the negative 6th meters, and that'll give us an answer of 6.03 times 10 to the negative 20 joules. Okay, and if we do the same thing for this one, I'm not going to rewrite the entire problem, but putting this in the calculator, you can do it one of two different ways. Just to keep life easy, I'll say 1.54 times 10, because they're micrometers, to the negative 9 meters. So again, I'm going to plug this in place of 3.3 in the denominator there. And if I do that, the value that'll come out is 1.29 times 10 to the negative 15 joules. So two different answers for that part. For part B, looking only at the wavelengths and any reference here, there happens to be something in the book, identify the region on the electromagnetic spectrum in which each of these belongs. So again, just as a reference point, I always like to think of, the whole 400 to 750, somewhere in that range, nanometers, and understanding what that is. It's times 10 to the negative 9. And then anything over on this side is longer wavelength. So again, I'll put over on this side, long wavelengths, and therefore low energy, lower relative. And then over here, you're going to have short wavelengths. Let's put wave. And higher energy, relative. And then think of some examples. What kind of things would be over here? Things like radio, infrared, and over here you're going to have UV and things like X-ray. Okay, if we look at these two, 3.3 micrometers. Okay, so if it's a micrometer, that's times 10 to the negative 6. So where would that fall over here? Is it within this range? No, it's longer. Times 10 to the negative 6 is longer than this one. So it's going to be somewhere, it's longer. So it's going to be over here, longer. It's going to be somewhere on this side. So probably IR-ish, something along those lines. So 3.3 micrometers times 10 to the negative 6 is going to be over here. This one here is still in nanometers, just like this, but 0.154 is smaller than 400. So I would imagine that would be somewhere over here because it's shorter than this range. So that's probably UV-ish, somewhere over in that range. Okay, let's do one more in this little section. 28. The energy from radiation can be used to cause a rupture in chemical bonds. A minimum energy of that is required to break the bond of a nitrogen-nitrogen N2 bond, triple bond. What is the longest wavelength of radiation that possesses the energy necessary to break the bond? Okay, so we know what the energy is. to break that. So we just started looking for the wavelength that goes along with that. And again, we can back up and take a look at this relationship. E equals hc nu, because we have the energy and we want wavelength. So these two guys can go together. We can simply just switch those two variables, just like this, wavelength, hc over energy, and then just plug everything over here and get an answer for wavelength. So let's do that. Lambda is equal to 6.626 times 10 to the negative 34. I'm going to cheat a little bit on this one and leave the units out, as long as I make sure that I'm using the right units. So for example, I have kilojoules here. This is in joules. So these guys have to be the same. I'm going to switch this bottom one to joules. The number I'm looking at here, searching for it, is this number here, but I got a small problem with this number here. It's 940 kilojoules per mole. This is based on photons, so I have to do a little bit of side work before I begin. So again, paying attention to the units that I put in here. So if I have, if I need a place to put it, I'm going to kind of squeeze it in down here. 941 kilojoules times 1 mole of photons, given the number that I have, which is 6.022, or this 2, I'll use that, times 10 to the 23rd atoms per mole. That's going to change my number here over to 1.56 times 10 to the negative 23. But the problem again is I still have kilojoules and I need joules. So if I have 1 times 10 to the negative 20, I put 23, 21, excuse me, 21 kilojoules per mole. I need to multiply times 3 to get from kilojoules to joules. So this number is going to get a magnitude of 3 higher. So let me start writing this over here, 1.56 times 10, and what number should I put up here? I have 21 kilojoules. I need joules. So times 1,000 should be 18. And this is joules now per photon. Hang on, I didn't put the other ones in there. The answer that's going to come out of this is 1.28 times 10 to the negative 7 meters. Okay. And you got to understand what this is. So that's not quite nanometers. If this is larger, somewhere in that range, what would I be looking at here? If I made it nanometers, this is kind of go that. So I'm going to make this smaller, which means I need to make this bigger. So it's going to be times 10 to the negative 9. So this got smaller. This number needs to get bigger. So 128 times 10 to the negative 9. So that's going to be something in nanometers. So what is that going to be? Going back to this example up here, somewhere a little smaller than 400. So I'd say it's probably UV, because it's something, again, a little smaller than 400. Okay. Let's probably call it quits on this one, and we'll start a new lecture for number 3.